Good day. I am RNJB Gilit from BSc 4A and I am going to discuss two problems regarding reinforced concrete design, specifically one-way slab as part of the activity of Compre 2 or comprehensive examination in design and construction. For problem number 1, a one-way slab has to carry a service live load of 4,000 Pascal. It has a length of 4 meters with both ends continuous. Assume that the compressive strength of concrete is 21 megapascal and the yield strength of steel is 415 megapascal for main bars and 276 megapascal for temperature bars. The steel cover is 20 mm and the unit weight of concrete is 23.5 kilonewton per cubic meter. Determine the required spacing of main bars. Let us first determine the given values in the problem. We have live load, and that is 4,000 Pascal. The length of the slab is 4 meters. Regarding concrete, its compressive strength or the FC prime is 21 megapascal. For the steel, its yield strength or Fy is 415 megapascal for main bars and 276 megapascal for temperature bars. The steel cover is 20 mm and the unit weight of concrete is 23.5 kilonewton per cubic meter. We are asked to find the spacing of the main bars. First, calculate the factored load. For live load, considering 1 meter strip, so the value of B is equal to 1000 millimeters. Then, converting the pressure live load into the uniformly distributed load. So, 4 kilopascal, and that is equal to 4 kilonewton per square meter, multiplied to 1 meter, since we considered 1 meter strip, and that is 4 kilonewtons per meter. Considering the minimum thickness of slab, and that is L over 28. L refers to length. Therefore, 4,000 millimeters divided by 28. The answer is 142.857 millimeters or 150 millimeters. Since it is dead load, it refers to the weight of the slab. So unit weight of concrete multiplied to the length of the strip, then to the height of the slab. Therefore, it is 3.525 kilopascal. Solving for the factor dead load and live load, based on the NSCP 2015, the factored load is 1.2 of dead load and 1.6 of live load. Substituting all the values computed, the factored load is 10.63 kilopascal. Then, for the effective depth, height of the slab subtracted to the concrete cover and 1/2 of the diameter of the main bars. So the effective depth is 124 millimeters. Meanwhile, the figure displays the maximum factored moment. This will be used to solve for the spacing of main bars at midspan and support. Solve for the spacing at midspan. Considering the ultimate moment is equal to the product of factored load and the square of the length of slab, divided by 16. And the answer is 10.63 kilopascal. Then, using the computed ultimate moment to solve for concrete design ratio or the variable R sub n, ultimate moment is equal to the product of reduction factor, concrete design ratio, length of the considered slab strip, and the square of the depth. The concrete design ratio is equal to 1.229044 megapascal. Finally, using the computed concrete design ratio, the reinforcement ratio can be computed. The computed reinforcement ratio should not exceed the minimum reinforcement ratio, so checking for it is necessary. Minimum reinforcement ratio is equal to 1.4 divided by yield strength of steel bars, specifically main bars. Then the computed value is 0.00337349. Since the minimum reinforcement ratio is greater than the value of computed reinforcement ratio, the minimum reinforcement ratio will be used. Then, computing the total cross-sectional area of steel bars, which is equal to reinforcement ratio multiplied to the length of strip of slab and the effective depth. The answer is 418 square millimeters. Finally, for the spacing is equal to the total cross-sectional area of steel bars divided by the cross-sectional area of a steel bar. Then, the answer is 270.568 millimeters or 270 millimeters. The computed spacing should not exceed the following parameters. The spacing should not exceed to 3 times the height of the slab and 450 millimeters. The answers are both 450 millimeters. Since the computed value is less than the maximum value, adopt 270 millimeters. The method in computing the required spacing at support is the same as the required spacing at midspan. The only difference is the computation of ultimate moment. Instead of the denominator being 16, it should be 10. The rest are the same. The computed value is also 270 millimeters. Based on the computed values, the required spacing for main bars, both bottom bars at midspan and top bars at support, is 270 millimeters. Similar to problem number 1, a one-way slab has to carry a service live load of 4,000 Pascal. It has a length of 4 meters with both ends continuous. Assume that the compressive strength of concrete is 21 megapascal and the yield strength of steel is 415 megapascal for main bars and 276 megapascal for temperature bars. The steel cover is 20 mm and the unit weight of concrete is 23.5 kN per cubic meters. Determine the required spacing of temperature bars. All the given values are similar to problem number 1. The only difference is we are asked to find the spacing of the temperature bars. Solving for the total cross-sectional area of temperature bars, and that is 0.002 multiplied to the length of the strip of slab and its depth, so 300 square millimeters. Therefore, the required spacing is the total cross-sectional area of steel bars divided by the cross-sectional area of steel bar. So, 261.799 millimeters or 260 millimeters. Again, the spacing should be checked based on the said parameters. Since the maximum spacing is greater than the computed spacing governs. So S is equal to 260 millimeters. Based on the calculated value, the required spacing of temperature bars is 260 millimeters.